Hello, my name is Rohan-Paul and very welcome to my computer vision and deep learning YouTube channel. Let's get started. So in this video, I will implement EfficientNet B0 pre-trained model with PyTorch, and the dataset I will use for this project is an image dataset of COVID-19 patients' X-rays from Kaggle, and it's a multi-class classification problem, and I will go through each step of the code in detail. Let's jump in. So starting with the code, here I am inside my Google Colab, and first few words on setting up the environment and installing some packages so you can run this notebook both in Google Colab or in inside your Kaggle kernel. So the first thing on the first cell, you can see that when I was inside my Kaggle kernel, I had to do a fresh installation of Torch and Torch Vision because the Torch Vision and Torch, that is a PyTorch that Kaggle already had, there was some version incompatibility inside that, and because of that, when I was pulling my dataset from Torch Vision, it was not working properly. But right now I'm inside my Google Colab, and here I did not have to reinstall the PyTorch or Torch Vision function packages, so I have commented them out. But in Google Colab, you have to install these image library called TIM. Super important. You most probably know it already. You have to use it everywhere in any computer vision project. So strangely, this was not there built in Google Colab, so I had to install it and just run the pip install TIM command in the first thing in the cell, and then check your of course in Google Colab for this project you have to switch on the GPU. Of course you can do without the GPU, but with this kind of project with lots of images and you have to run models like deep learning models like EfficientNet or something similar, you do get a lot of benefit with GPU switched on. So you just do runtime, change runtime type, and there you select your GPU. And then to check what kind of GPU you got, just run this command NVIDIA-SMI, and that will give you the details of the GPU. So in my case, I got allocated a Tesla P100 with a virtual RAM of 16.280 MB, that is 16 GB virtual RAM. All right, that's and CUDA version is 11.2. Okay, so that look really good actually. All right. And of course, I have to mention that this is a Colab Pro version because I subscribe to that. So sometime if you are a Colab free, if you're using Colab free version, that you may not get P100, but sometime you may get a Tesla P100. But anyway, if you do not get what you want, actually, you can do the factory reset of this notebook by doing runtime factory reset runtime. If you do a couple of times and check again and again what kind of NVIDIA SMI get, accordingly sometime you get a better GPU. All right, so that's setting up the environment, and then this is where my actual code starts. So the first cell is all the standard imports. So I'm using PyTorch for this project. So Torch Vision, then torch.nn module. I definitely have to use the standard modules like data loader and etc. Torch Vision import models. And all right, and I'm using these copy module or copy package for making some deep copy that I will be using in this project. And apart from that, the standard again, the warnings and warnings.filter warnings ignore. And then this is an important line, very standard and very common in many computer vision projects, that you have to set your device. So if CUDA is available, then set it to CUDA, else CPU. So just in case you are running your this project in your local machine and your local machine does not have a GPU, or the GPU is not powerful enough, because for GPU to be compatible with PyTorch, you need the GPU to have a compute capability of at least I think 3.5 or something. So a 4 GB or 6 GB GPU, although that's normally good enough, but that is not compatible with PyTorch. So in that case, you can set the device to be CPU, and then in that case, you just comment out this line and just manually set your device to be CPU. And then the next important thing is I have to check the version of my Torch and Torch Vision. And here I can see that for the PyTorch I got 1.10 with CU11, and so is my Torch Vision also is CUDA 11, and 0.11.1 is a version of Torch Vision. All right, now that then in this cell I am actually defining all my root path variable. That's a common step I do for all my computer vision project, that because many of these computer vision project involve lot of image files, so they need to be run sometime in Kaggle kernel, sometime in Colab virtual machines own session storage. But most common way that I take is that I keep all my image files in Google Drive, and then I have my notebook running in Colab, and then the Colab access these big image folder data, that is input training, the whole training data set of images from my Google Drive. And that's what this root path is defining here, that I am connecting my Google Drive data set here. And that will bring the Google Drive dataset to my Colab here. And to connect it, that's a very simple process. You just have to right now I'm not getting it, too many session. Okay, I have another Colab running, so I cannot run it here again. All right, so there's an icon when you go here. There's an icon for Google Drive. You just click on it, and then it gives you a prompt that if you want to where you have to select your Google account, and then it will be connected. Otherwise, if you just want to write the code, this is the code, very standard. Everybody uses it from google.colab, import drive, and then drive.mount content/drive, and that will mount your Google Drive. All right, in my case, it's this is how I mounted the drive. All right, that was my entire initial setup, and now the actual code. So first, let's quickly go to the dataset that I'll be using for this. So this is my dataset that I'll be using for this notebook, that COVID-19 image dataset. It's available in Kaggle. So if you just search for COVID-19 image dataset, and you will get this 170 megabytes, pretty small indeed, COVID-19 dataset. And else I will definitely give the link in the description section of this video. So this dataset is I chose this dataset just because mainly the reason is that it's pretty small, so you can quickly run your notebook very fast. The epochs will be over probably in each 1 minute or 1.5 minutes. So this dataset has two subfolders, test and train. And if you go inside the train folder, I have three classes, COVID, normal, and viral pneumonia. And similarly, under the test dataset, I have the same classes, COVID, normal, and viral pneumonia. So if you go inside, say for example, inside train, I'm going inside COVID, there's a lot of images, all of X-ray images of patients like this, and the same structure is followed by the test folder as well. So if you go inside COVID, you will get many images. If you go inside normal, you get all these images. So these COVID, normal, and viral pneumonia, these are the three classes for this project or for this dataset. And our task is to classify our model according to these classes. So when at the end of the notebook, when I do my evaluation, I will be passing to my model this test data set and see that how many my model correctly predicts to be within these three subclasses. So coming back to my Colab, the first thing I want to do is what we saw in this dataset. I just want to plot few of these images and inside my Colab notebook. So first what I'm doing is I'm just defining all these path variables. So my train directory is wes.path.join root path, and then I'm passing the train here because I have inside the root. So inside, this is my root path, and inside that I have a test and I have a train, and inside the train itself I have all these three classes. So that's exactly what I am emulating here that train COVID directory will be my train directory, which is this, and to that I have to join COVID, and train normal directory will be train directory join normal. Similarly, the train pneumonia directory will be os.path.join train directory. To that I have to join viral pneumonia. I think I did it right. Just quickly check. Yes, viral pneumonia. There's a space between viral and pneumonia. All right, and then with that I am getting all the file names by using os.listdir, and then passing to that these train this COVID, normal, and pneumonia. This will give me all the file names, and you can quickly check it. So that's what I'm doing in the these 3 lines. I'm just printing these 3 variables which should contain all my file names. So I'm printing just the first 10 of them. So this is the result. I got one list for my train COVID F names, that is list of 10 elements, 01.jpg, 010.png, jpeg, jpeg, and similarly I'm getting another list for my train normal file names, that is train normal file names, and similarly for the last one I'm getting all the pneumonia file names here. And remember, again, this is just the first 10 elements because I'm choosing here only the first 10. All right, now I need to plot some of the photos, some of the images, and for that I am going to have a number of rows of 6 and number of columns 4. That's what I'm defining, and then I am using figure.set size inches, number of calls into 4 and rows into 4, and picture index, I am just initially I initialize this peak index to be 0, index for iterating over the images, and then I'm increasing it by 8. And just to check that this gives me kind of what I want, I am just printing out the entire path, COVID image path list. This variable should contain the entire path starting from the root, starting from the entire path directory actually. That is, if I pass this path, my Python code should be able to get the image. So it's an absolute path, not a relative path. So that's what I'm doing here, os.path.join train COVID dir f name. For f name in train COVID f name, peak index -8 and then peak index. So from -8, I'm choosing from -8 index to peak index, like this, sorry. Yeah. So, and then that COVID image path should have these 8 images full absolute path names, and that's what I get here. 1, 2, 3, 4, 5, 6, 7, 8. Yes, I got 8 of them because that's what I chose here by selecting the index from peak index -8 to peak index, and then I'm just printing COVID image path list. So that will give me the list of the full absolute path of 8 images. And exactly in the similar way I have to do for my normal images and also viral pneumonia images. So this cell was just for checking that that this is working, and then I can actually comment them out, because in my next cell I have the comprehensive code for all this together. So in the next cell, what I'm doing again, it is just what we already discussed, that n rows and n columns I'm defining to be 6 and 4 respectively. And then I am defining 3 path variables: COVID image path list, normal image path list, and pneumonia image path list, with exactly the similar kind of code. Only thing I'm changing is for COVID, I'm taking the file names from train COVID names here. For normal image list, I'm taking the file names from train normal frames, and for pneumonia image list, I'm taking the file names from train pneumonia file names. And then for each of them I am selecting 8 images only, and that I am defining here inside this third bracket, peak index -8 to peak index, inside this square bracket indeed. All right, and now simple, you just need to plot them with plt.im show. So I'm just running a loop for I in image path. In enumerate, I'm enumerating over all these three variables. So I have my three variables: COVID image path list, normal image path list, and pneumonia image path list. So I'm enumerating over them, and then I am creating a subplot here, plt.subplot, and to that subplot I'm passing the n rows and n columns that has already been defined at the top, keeping the axis to off because I do not want to show the axis or the grid lines. And then finally just image equal to mpimage.im read, image read. I'm passing to im read, I'm passing these image path, which is this image path is actually each of these element. So each of these is an image path. And then finally plt.im show image, and then plt.show will give me these images. So these are just some plotting. This is the output of them. All right, so I just plotted 4 by 6, 6 by 4 matrix of images. All right, that was just for visually checking that it's all the images are coming properly in my notebook. There is really nothing, no particular conclusion to be drawn from this cell. All right, so that was the initial step. I did not do any EDA here because here the main purpose of this notebook is to implement the efficient net B0 pre-trained model, and not to do the EDA. So that's the reason I did not do much of EDA, but definitely in a full project you have to do some EDA to understand the data better. All right, now coming back to our code, and so the first step of almost any computer vision or any deep learning project in PyTorch, you have to make your dataset loader function, and that's what I'll be doing here in this cell. That I have a function named getDatasetLoader, and that will load my dataset on a batch by batch basis, and of course applying some transformation. So let's quickly understand this getDatasetLoader function because it has a couple of sections. The first section is a transformation. Here I do all my data augmentation part of the original images. Generally, transformation does help the model to prevent the overfitting issue, and that's what I'm doing. I'm applying various methods like random horizontal flip, random vertical flip, all these things to change my original training images and bring in much more variety into my training images. For example, this random horizontal flip will flip the image horizontally with a given probability, and the probability here I mention is p equal to 0.5, and then in the random vertical flip it is just the same thing, but here the image will be randomly flipped vertically. Then I have random rotation I'm not using here. So random rotation, just like these two, random rotation transforms or rotates the image randomly by an angle. The angle normally is given in degrees, but I'm not using random rotation here. Do I? No, I'm not. All right, I could have used random rotation as well here. And further, I'm using these random erasing that will again randomly erase some of the pictures and part of the pictures with a given probability, which I'm mentioning here as p equal to 0.12. Then in center crop, this method will crop the image at the center, and if the image size is smaller than the output size along any edge, then in that case the image is padded with 0, and then it is center cropped. And what else? So I'm also applying normalize. This is very important. So see, in the normalize, the images will be scaled and normalized, but why I'm using these specific numbers here. First, quickly understand what normalization means. Let's get the formula first. So here in this cell, I'm just including the formula for normalization. So what it will do is that the original input, the normalized input channel will be the original input channel minus mean of the channel divided by standard deviation of the channel. So that's how my original value will be transformed to give me the scaled value, that is this left hand side expression, that will be my normalized value. And so what the statistics metric that I need for this is my mean of the data and a standard deviation of the data. So in PyTorch, this is the value that is recommended in their official documentation. So this whole thing, this is the mean, and then this tuple, this is the standard deviation. Now, why exactly these values only? And that's because these mean and standard deviation values that you see here for our normalized function, these values are calculated based on the famous ImageNet dataset, and that's a huge dataset containing millions of images from a variety of sources. So in many standard projects, using the ImageNet datasets, mean and standard deviation is a common practice. Of course, if you want, you can use your own custom datasets, own mean and standard deviation, but most of the cases using these ImageNet mean and standard deviation will give you pretty standard result to start with. And further on this point, that whether or not to use ImageNet's mean and standard deviation depends on your training data. Assuming your data are ordinary photos or ordinary images of natural scenes, for example, people, buildings, animals, and varied lighting, angle, background, etc. And assuming your dataset is also biased in the same way ImageNet dataset is in terms of class balance, then it's okay to normalize with ImageNet's scene statistics, which is what I'm doing here. But if your photos or images are special somehow, for example, color filtered or contrast adjusted or uncommon lighting, etc., or they are unnatural subject or specialized subject, for example, satellite imagery or hand drawing, then you probably need to experiment with the respective training datasets, own mean and standard deviation for normalizing it. So these actually, for this project, the dataset that I have used is for COVID-19 patients' X-ray images. So actually, they are also of specialized nature. They are don't exactly conform to the overall kind of situation that ImageNet dataset conform to. But I use some other mean and standard deviation, and overall, I was getting better accuracy with the ImageNet's mean and standard deviation usages. So anyway, this model is a base model, and after I get my base accuracy and base prediction right, then I may experiment using the mean and standard deviation of different numbers. And in case you are using a new mean and variance from your own training dataset, don't forget to scale the validation set and test set using the mean and variance of the training set rather than their own mean and variance, because otherwise you will introduce a domain shift. And what is domain shift? Domain shift refers to the differences in the data distribution of two datasets, normally between the training set and the test set. So even if you are using a separate mean and variance, then use the same values of mean and variance for your test and validation set as well that you are using for your training set. All right, now going back to this function get dataset loader. So after I do all my transformation, then I do this line, very important, very standard, that I'm using datasets.image folder, hugely useful function. So this function is such a beautiful and so useful that you just pass a path of your whole training input images and apply the transform as a second argument, and then you will get your data beautifully segregated as per labels. And the only requirement for these image folder function is that your input training data should be in different folder per label for this default function to work. What I mean is that, let's go back to our data set. So in our dataset, let's check this train subfolder. I have COVID, normal, and viral pneumonia. So these are the three classes, and all these data under the all images under COVID is actually representing COVID. All images under normal representing normal X-rays, and all images under the viral pneumonia representing the images which have been segregated as viral pneumonia. So what it does is that all the images are already segregated by its labels, and that's the only requirement for your image folder, this function to work. And to this you just pass the root path. My root path was the original training, the whole this root path, and then to that you have to join the train, because I am fetching data from the train folder. And then this function will return me the randomly selected and transformed batch of images with corresponding labels. It just works beautifully. And next, what I'm doing is I'm splitting my training dataset between training and validation. So I am deciding on the length of my training images. So I'm taking 78% of my total dataset to be the length for training, and the rest of that is this line. After selecting the 78% for my training indices, the rest of the data should be my validation, and that is defined as len validation images. And then I'm applying this random split function. The random split will give me the random training and validation dataset from my these two length. So to the random split function I pass the entire training images, which is my this one that is being returned from the image folder, and the second argument I pass a list, and the list only mentions my number of, that is the length of the training images and length of validation images, and the random split will do its job internally. And after I get my train data set, then my job is almost done. Now the final thing, I have to apply the data loader function, the super important data loader function. It will to the data loader I pass this train data set, and then few other parameters to control that how the batches are created and will be fetched and passed to the training model. So after my training data set, as a first argument, I just give the batch size, which may be 32, 64, 128, and so on. Shuffle, I'm also keeping it a true. It will shuffle the dataset. Number of workers, that is a number of CPU cores that will be engaged during your data loading. So that I'm passing it a 2. If you want to apply many more, you can of course do that. All right, that's my train data loader, and exactly similar code for my validation data loader as well. As a first argument, I'm passing the validation data set, then batch size, shuffle, etc. And finally, I'm returning the train data loader, validation data loader, and the length of train data set and the length of validation data set. So this entire thing is done within an if loop, and that is here at the top. So because the same get dataset loader I will be using to get my data loader both for my training set, and also I'll be using it for my evaluation stage. That is when I'll be fetching my data loader from the test set of dataset. Remember, our original dataset has train and test. So that's why in these function I have a parameter called train, which is by default will take false. And so if train is true, then this whole thing will execute. Otherwise, if it is false, that is when I'm in my evaluation phase and I need to fetch my data from the test set, then this else block will get executed. And what is the else block? The transforms remains almost the same. Only thing I'm changing here is that here I do not want to do random splitting, and I'm also not doing, what else I'm not doing, image folder I'm doing, random splitting is the only thing that I'm not doing. So here I'm just doing the data transformation as I was doing in the train block as well, then pulling my all my images with the image folder, then and that's it. That's pretty much it. And then finally I'm just loading my test data loader, applying data loader function, and then finally returning the test data loader and also the length of the test images. So that was my test get data loader function. This cell was just for showing a thing, so I can delete this one. And so here the get the number of classes is just simple. I'm just so my number of classes you already saw. There are just 3 classes: COVID, normal, viral, pneumonia, and that's what I'm doing in this cell. I'm just getting programmatically the number of classes from the dataset.image folder dot classes. This is the thing that you, when from the image folder on the return value of the image folder, if you do a dot classes, it will give you the class names, and on that you can just apply len to get the number. And then I'm displaying a random image that to see that it's really still working. So now instead of fetching from my original path of the dataset, here I'm displaying the image from the return value of this image folder function. So train data equal to dataset.image folder and os.path.join, etc. That's normal. And then from this train data, I'm just selecting a random image 2 and then 0, and that's perfectly displaying the image. One quick thing I forgot to mention in the transform section of my get dataset loader is that I applied a resize of 256, and the reason of that is because if you go to the official code in Torch Vision for EfficientNet B0 pretend model, they are actually recommending some recommended shapes for B0, B1, B2, etc. I have actually taken this part of the code from the official documentation that when EfficientNet B0 pretend model is applied, it expects the shapes to be at least 256 by 224, and for B1, that is EfficientNet B1, it requires 256 by 240, and so on for various B2, B3, B5, B6, etc. all of this. So for B0 I need 256 by 224, so that's the reason I am doing a resize of 256 here. All right, now moving on. You are done till here. All right, now those get dataset loader is done. So now I want to invoke that get dataset loader function to get all my loaders. So this cell is just doing that I'm invoking or executing this get dataset loader function with the root path. Batch size I am defining it to be 32. Train equal to true, and that will give me the train data loader, validation data loader, len train data loader, and len now validation data loader as a tuple. And similarly I am doing that for the test dataset as well. So only change I have to make is train, I have to keep it as false, and that will give me test data loader and len of test data loader. And then if you after getting these things, I just wanted to see that what they actually give me. So if you print train dataset, train data loader dot dataset, you will get it as this is an object of torch.utils.data.dataset. And if you do the same for test data loader dot dataset, I am getting this entire thing. So I have my root location, and then all these compose that were all these resize and other transformation that was applied here. All right, let's move on. And in this cell I'm just printing the length of all these various data sets: train data loader, validation data loader, and similarly print len of test data loader. And yeah, moving on, I am defining a quick thing here. It will be a quick dictionary I'm defining here, and it will be very important while in the training phase. That is during the training, we will see in a second that our training will be executing both the whole function both on my train dataset and also on my validation dataset within each epoch. And to do that correctly, this kind of dictionary is required. I have also seen this same practice being observed by many well-known repositories in GitHub and also many well-known projects, that we define a dictionary and then I define two keys here: train validation, and the train key will have my train data loader as its value, and the validation will of course have the validation data loader as its value. And the second dictionary will just return me the length. It's just the same structure, train and validation, but instead of the data loader, it will give me the length of the data loader. All right, we'll see the usage of this dictionary, this dict, in a second. And before starting the training, after here, just quickly, I'm plotting the images, some of the images randomly, to see the images after the augmentation is done, because previously when you plotted, the augmentation was not included here. This was the original images as it was given in our data set. So now all my augmentation have been applied, and I have my data fetched with this data loader. So I have my train data loader, test data loader, etc. So now I want to plot them to see how they are coming up. And hence for plotting in this cell, I am doing this quick little thing, that I'm applying iter method on my train data loader. So this train data loader that was returned from get dataset loader function is a Python iterator, and when you pass this train data loader to the iter method, it will return you an iterator that you can iterate over. That's exactly what I'm doing here. And then when you get these iterator, that is this variable train loader iterable, you can apply the .next on it to get my images and labels. So basically these, I have made a note here that this train data loader will return elements from your data set batch by batch. This allows you to use it for data in train loader, and the next method then calls the __next __ method on the iterator to get the first iteration. And if you run next again, you will get the second item of the iterator. Yeah, so that's how it works. So and that's what exactly I'm doing. Images labels from train loader iterable .next. Now that for displaying, I have to convert the images to numpy. So the next line, just applying the numpy function. And then it's simple, just plotting it with a little loop over here for index in np.arange 20, because I'm plotting 20 images. Add a subplot, define few parameters here, xticks, yticks, etc. And then im show np.transport image index 1 to 0, and set title. Yeah, so that will give me these images. And how I'm getting this title is because I am fetching this title from class categories, labels, index. Remember, we already defined our class categories here. Where was that? One second. Yes, class categories we defined here, datasets.image folder. From that, I only pulled the classes. That's my class categories, and class categories is just this single list: COVID, normal, viral pneumonia. So here for the plotting, I'm getting my class categories as well by their index. Class categories, labels, index. All right, now, so that was my plotting, and all these images, the difference you see is because of all the augmentation and all the transformations that were applied. They're also normalized, they're resized, and these little box that you can see where the image has been deleted, kind of, that was because of that random, what was that? One second. I think I applied random erase or something. Yes, random erasing. So that erasing is because of the random erasing function. All right, that was all about our preparing our data and knowing our data. And now I'm ready to load my EfficientNet B0 pre-trained model from Torch Vision's model module. Oh, I forgot to mention quick and actually quite important things. Um, that is the meaning and significance of this line, that why did I use 120 over here to get my images. And I really want to explain it well, because in deep learning and computer vision projects, it's all about shapes. In so many times and so many projects, you really have to put a lot of effort in making your shapes and sizes compatible and meaningful. Otherwise, the whole model will just fall apart. So the reason of using, before understanding why did I use 120, let's look at the sizes of my images and labels. That is what is returned from my data loader function. So here I printed them already, that for I and inputs and labels, which is a tuple, in enumerate train data loader. Remember, train data loader was the output from my data loader function. And now I'm just printing the shapes of them. So my inputs are shaped like this. Each is 32, 3, 24, 224 by 224. And then my labels are all of size, each of them of single scalar vector. That is, I mean, each vector has a single element, 32. Now, let's look at this first one, the shape of the image. Here, 32, this first one, it denotes a number of batches. Then 3 is a number of channels, and 224 and by 224 is the height and width respectively. Now, for all of these, I'm getting exactly same. For the last batch, I'm getting 3, because only 3 more batches are left after taking all these batches. So from my total data set, and that's why I'm getting the 3, because this just denotes leftover number of images. So this is how PyTorch outputs your train data loader. And for the labels, because labels is just a single scalar value, that is between our labels. Remember again, what was our data, what was our labels? That's just 3 values: COVID, normal, and viral pneumonia. So 0, 1, 2, that was our labels. And so this label can take only a single scalar value, and I'm only getting 32 because it just denotes a number of batches here. Now, when in this cell, I'm also printing the labels list here, and let's see what this labels list is. Okay, did not run. Let's run it. Okay, in the meantime, we'll come back to this labels thing after a second. Before that, to understand our primary thing, that why did I use 120 over here, I found a beautiful Stack Overflow answer to explain this whole thing. I cannot answer it better than that. So just refer to this Stack Overflow question here. So original question was asked these, that how do I turn my PyTorch data loader into a NumPy array to display image data with matplotlib. And that's exactly what I was doing here as well. That is, I got my train data loader returned from this data loader method, then I converted it to NumPy array and then displayed the images. So let's look at this answer, and that will explain it all. So first of all, data loader outputs 4-dimensional tensor: batch, channel, height, width, and that's exactly we talked about. Now that this shape of these input images, this is batch, channel, height, width, batch, channel, height, width. Each of them are shaped like this. And now that's how the data loader output. It's a 4-dimensional tensor of batch, channel, height, width. But matplotlib and other image processing libraries often requires height, width, and channel. So you have to convert this channel, height, width to height, width, and channel. And there will be a lot of images in your images. So first you need to pick one. This will simply be image I, which is what I'm doing as well. When I'm running the loop here, that is, I'm iterating over the entire NumPy entire images. For each image, I am doing image IDX. So that is, I'm actually capturing each image. That means now this image IDX will not have this batch dimension here. So this will be a three-dimensional vector containing only channel, height, and width. So this will not have the batch dimension. Batch dimension was there when I was printing my entire images. That is the whole here inputs is actually these input images. So when I was printing inputs images dot shape, that was having this batch number as one dimension as well. But now inside this loop, images index will not have the batch dimensional. I'll be left with channel, height, width. But matplotlib wants height, width, and channel. And that's why your transpose should convert now channel, height, width tensor to a height, width, channel tensor. To do so, use np.transpose image.numpy and 120. And that's exactly what I was doing. And that's exactly the reason that I had to choose 120 with the transpose. Here 120, and that's the reason that I was actually converting my channel height width to a height width channel to be compatible with matplotlib. Meaning this 1 is my height, 2 is my width, and 0 was my channel. And now it is compatible with matplotlib, and so this plt.im show can recognize this to be an image and plot it, because now I have height as the first dimension, then width, and then the channel. And that's how I converted my channel height width tensor to a height width channel 1. All right, and now coming back to the list and the labels list parameter here. So check out this last line, that the way that I was getting these class category names in my displayed images, that is COVID, normal, viral, pneumonia, etc. So these labels is an array here. In this case, I was just selecting 20 images, so it will be a list of 20 elements, and the elements will all consist of 0, 1, 2. And this is that list, because I'm printing it here. Label list is labels, and this is my labels list. So it is an element of 20. It's a list of 20 elements, and each element is between 0, 1, 2, because that is the value of my class categories, and that is COVID, normal, and viral pneumonia. So in this line, I'm just getting these value from these labels. That is, if my IDX is 2, so for example, my IDX is 3, for example, just to give something different from 0, 1, 2. IDX is 3 means 0, 1, 2, 3. This one, that is a value of 2. And 2 means it's viral pneumonia based on our class categories. Again, our class categories are this: COVID, normal, viral pneumonia. COVID is 0, normal is 1, viral pneumonia is 2. All right, and so that's how I was getting my, that's how this line makes sense, and that's how this line was setting the title in this plot by fetching the class names. All right, that completes my explanation of that section. Now let's start off with the actual part, which is EfficientNet B0 model from pre-trained Torch Vision model training. And before defining the model, the first thing I do is this line, torch.backends.cudnn.benchmark equal to true. And what does this line do? It enables benchmark mode in CUDNN, and so allowing you to enable the inbuilt CUDNN auto tuner to find the best algorithms to use for your hardware. Benchmark mode is very good whenever your input sizes for your network do not change. This way, CUDNN will look for the optimal set of algorithms for that particular configuration, which takes some time indeed. And this usually leads to faster runtime. And when I say that the input size for your network must be same, it means that the images that you input to your model, say EfficientNet B0 here or ResNet 50 for that matter, should be the same size at every iteration for maximum performance. By changing input size, I am not referring to the size of images that the data loader reads from your input folder or image folder. I am referring to the output image from the data loader. And so it is fine to resize your images at every iteration, even with benchmark equal to true. That is cudnn.benchmark equal to true. So when you enable this line, that is cudnn.benchmark equal to true, what it does is before beginning the training of your model, it optimizes your model based on your inputs for maximum performance on the GPU. That is why when you start training with this benchmark equal to true, it takes some time before the actual training starts. But if your input size changes at each iteration, then cudnn will benchmark every time a new size appears, and possibly leading to worse runtime performance in that case. And that's why it's so much important that your input sizes does not change in every iteration, because in that case each new input shape will rerun cudnn find function to find the fastest kernel for this shape, and so this will add to your time to execute. So if your input always have the same size, you should enable it all the time. That is keeping this line at the very start before your model building function. And so when it cannot be used, some examples of that would be if you have layers that are only activated when certain conditions are met, or you have layers inside a loop that can be iterated a different number of times. These are some basic examples when you should not have this line. And because I am using the pre-trained EfficientNet B0 model, this is the key defining line, that is model equal to models.EfficientNet B0 pre-trained equal to true. And EfficientNet B0 is what I have already imported at the very top. Let's quickly see the line. That line is where is my models from Torch Vision .models. Yeah. So this line, Torch Vision imports models, and that's from this module I'm importing the EfficientNet B0. Let's go back to my line. Yes, and so this is a pretend one, and if I print this line, that is model.classifier is model.classifier, this will give me all the parameters inside it. So this line will actually print, give me this place. Let me see if it's, yeah, indeed. Model.classifier is, yeah, sequential dropout with a p equal to 0.2 in place true, linear in features is 1280, out features 1000, and bias true. All right. Okay, so that's my pre-trained model. And now because I'm using a pre-trained model, so the first thing I do is I run this little loop for param in model.parameters, param.recurse grad equal to false. So what this does is that if you want to freeze part of your model and train the rest, you can set this recurse grad attribute to false. And when dealing with pre-trained models, it is important to freeze the computational base before you compile and train the model. Freezing, that is by setting recurse grad equal to false, prevents the weights in these given layers from being updated during the training. And basically, why do I want to do this? Because I'm using a pre-trained model. They have already been trained. All their weights have already been adjusted and have gone through probably millions of gradient adjustment. So I no more want that to happen now, because I'm using that fully trained pre-trained model here. All right, and now for my number of inputs, I'm just taking from my pre-trained model the in features. Remember, when I printed this model.classifier, it gave me this output. So this is my classifier. So now from this classifier, I am taking this one, that is at 1th position, and I'm taking only in features, which is 1280 in this case. All right, so that was my pre-trained model kept in this variable model, and to this pre-trained model I am adding some new layers, and these I'm defining here. That is model.classifier. So this variable model has already been defined from my pre-trained FNet model, FNet B0, and to that now I'm adding some new layers, and which are nn.sequential, and then I'm adding a linear SILU layer, that is sigmoid weighted linear unit, and then a dropout with a 0.2, and lastly my last layer is also a last linear layer. And note that this linear layer will have 2048 into number of classes, and so that's why I am reshaping these final layer to have the same number of outputs as the number of classes in my training dataset, which has already been defined as class categories, and I'm just taking the length of this. And again, what is this length? It's just 3, because I have only 3 classes in my training dataset. And finally, after these new layers have been added to my original pre-trained model, then I am transferring this model to my device. That is keeping this tensor to my device, and device has been defined to be GPU or CPU according to whichever is available. And now if I print this print.model, what I will get is this, that is sequential, then it's a linear SILU dropout linear. Okay, and now I have to define some more variable criterion, because this is a multi-class classification problem. I have 3 classes, so I am using cross entropy with a label smoothing of 0.11, and criterion also I am I'll talk about this level smoothing in slightly more detail in a second. Before that, then after defining the criterion, I'm transferring this tensor as well to the device, because all my model training related tensor should remain in the same device, else you will face a lot of problem. And finally, my optimizer I'm choosing to be AdamW, which I am getting from optim module of PyTorch, and then .AdamW, and to that I'm passing all my model parameters and learning rate of 0.001. Now coming back to this level smoothing, let's know it a little bit more detail. So label smoothing in a nutshell is a way to make your model more robust so that it generalizes well. And the fundamental problem that the label smoothing solves is a problem of overconfidence, and that is solved by calibrating the model with label smoothing. So what is an overconfident model? An overconfident model is not calibrated, and its predicted probabilities are consistently higher than the accuracy. For example, an overconfident model may predict some test input to be with a probability of 0.9, whereas the accuracy is only 0.6. And note that models with small test errors can still be overconfident, and therefore generally you benefit by bringing in a label smoothing factor here. So the formula for label smoothing is just this, that label smoothing replaces one hot encoded label vector y hot with this is my y hot with a mixture of y hot and the uniform distribution. So here is a formula. My on the left hand side expression did y underscore ls, that stands for the label smoothed y value, and that is equal to 1 minus alpha multiplied by my original input vector, that is one hot encoded label vector y hot, plus alpha divided by k. And here the k is the number of label classes, and alpha is a hyperparameter that determines the amount of smoothing. So if alpha equal to 0, we obtain the original one hot encoded y hot, and if alpha equal to 1, we get the uniform distribution. So normally, here for these alpha, I have taken the value of 0.11. It's a pretty common value for alpha, and I got good result with these 0.11 value. That is my overall prediction and accuracy result was satisfactory. So label smoothing is used when the loss function is cross entropy and the model applies the softmax function to the penultimate layer's logit vector to compute its probabilities. And the problem, one hot encoded label that we get is that one hot encoded labels encourages largest possible logit gaps to be fed into the softmax function. Let's see a quick example if that makes sense. All right, in this example, say my logit vector is these vector 10 0 0, and applying softmax to this gives me 0.999900 rounded to 4 decimal places. Now if we use label smoothing with an alpha of 0.1, the same logic vector becomes 3.332200, and the smoothed label vector after softmax becomes 0.9333, 0.0333, 0.0333. So what you notice is that the smooth label vector after softmax has a smaller gap, and this is why we call label smoothing a regularization technique, as it restrains the largest logit from becoming much bigger than the rest. And why these large logit gaps is a problem is because intuitively large logit gaps combined with the bounded gradient will make the model less adaptive and too confident about its predictions. In contrast, smooth labels encourages small logit gaps, and actually there has been a paper published, you can just Google search it, that it has been shown that these smaller logit gaps actually results in better model calibration and prevents overconfident prediction. So overall, whenever a classification neural network suffers from overfitting and or overconfidence, we can try label smoothing. And just like, and how do I choose the value of the hyperparameter alpha? Just like other regularization hyperparameters, there is no formula for choosing the best alpha. It is usually done by trial and error, and normally alpha equal to 0.1 is a good place to start. And then I'm creating and defining a learning rate scheduler with these PyTorch module optim.lerscheduler.step_ler. So this is a method that I'm using for this purpose here. So basically this will change the learning rate based on number of epochs, and the hyperparameters that it will take, the step LR will take our step size and gamma. So how this works is that it decays the learning rate of each parameter group by gamma every step size epoch. So here my step size is 3. That means it will decay the learning rate by for every parameter group by this gamma value every 3 epochs. And then I am creating two variables, training history and validation history, that will hold my the training and validation history accuracy and loss as a dict. And then finally my training starts in this cell. So this is a function that I'm first creating for the entire training, and then after this cell I will just invoke this training function like this, that is model trained equal to train, and then pass all the arguments. So let's understand very well what this training function is doing. So first, to start off, it takes, obviously the first parameter, it takes a model, then criterion, which is my kind of loss function, optimizer, scheduler, number of epochs by default it takes, but of course you can give much higher. And I'm also giving a start time that will be defined by time just now, and so that at the end of my training I am also updating the start time. I think somewhere here, yes, time elapsed equal to time.time minus start time, so that I can just check that how long the entire training took. All right, now and first I'm choosing the this is a pretend model. We already know that we are using the Torch Vision's efficient net B0 pretend model. So first I am defining a variable to hold the best model weights by doing a deep copy of this model, and with its state dict. The state dict is simply a Python dictionary object, and this maps each layer to its parameter tensor, because state object or Python dictionaries, they can be easily saved, updated, altered, and restored, adding a great deal of modularity to PyTorch models and optimizers. Note that only layers with learnable parameters, that is convolutional layers, linear layers, etc., are registered buffers and have entries in the model state dict. And what is the difference of state dicts with the model.parameters? So I have model.stateDict and I also have model.parameters. And what is the difference? The parameters only gives the module parameters, that is weights and biases. On the other hand, stateDict returns a dictionary containing a whole state of the model. PyTorch internally relies on Python's pickle module, and Python dictionary can easily be pickled, unpickled, updated, and restored, and thus saving model using stateDict offers more flexibility. You can also save the optimizer state, hyperparameters, etc. as key value pairs along with the model stateDict, and when restored, you can access them just like your usual Python dictionary. So this stateDict you will see many times in any computer vision, any deep learning project with PyTorch, because this is also the recommended method or recommended way to save your model for getting everything from the model in future for some other purpose. So anyway, that was about stateDict. So I'm just defining my best model weights to be model.copy.deepcopy and then model.stateDict. And then best accuracy, I'm initializing this value to be 0.0, and then gradually over the when I'm training batch by batch, I will update both these variables that we will see in a second. So as usual, I start the epoch with a loop here for epoch in range num epochs, and then I'm just printing some basic values to see that visually when I'm updating my epochs. And as a very first step inside my epoch, inside the loop for the epoch, I am configuring my train and validation phase. So under the first epoch or under any epoch, the first thing I'll do is run this little loop here. That is this loop will run for train and the next it will run for validation, for phase in train and validation. And then if the phase is train, then I'll be doing model.train, else I'll be doing model.eval. So model.train pretty much tells your model that you are in training mode. So effectively layers like dropout, batch norm, etc., which behave differently on the train and test procedures, know what is going on and hence can behave accordingly. So remember that after I start this for loop, that is it will traverse through train and then through validation. Then after I start this loop, the entire rest of this code within my train function, it goes on or it get executed within this for loop, meaning all these codes will run once for train phase and then for validation phase. And also during the execution at various stage, I have to pass if the phase is train or the phase is the other one, that is a validation one. Anyway, so let's move on. The first thing after this phase has been configured, then I am doing a running loss. I'm creating two variables to define my running loss and running corrects, and I'm initiating them both with zeros, and obviously I will update them with each epoch and each batch loss. And then after for epoch in range, then I start another loop for input labels in tcudm data loaders dict phase. And what is my data loader dict? We already have defined it sometime earlier. Let's quickly get it, because I'm going to use this data loader so many times during my training function. Yes, here. Let's just copy it, and just for quick reference, keep it here, because I am going to refer it many number of times. All right, so this is my data loaders dict that I have already defined, and it has two keys. It is a key value, that is train and validation, and that's exactly what I'm looping through in my this loop, that is for phase in train validation. So when I'm doing data loaders dict phase, effectively what this is doing is hold this below loop, that is for inputs labels in DQDM data loader dict phase, and then I do all my calculation inside it. Indeed, all these basically means is that for every epoch, the train data loader and then the validation data loaders is invoked, which returns input and its corresponding label. So because I'm looping through phase will take two values, train and validation. That means first my train data loader will be calculated, and all the code execution will be done on my train data loader, and then validation data loader. All right, let's do that. And just like previously, we put our all our important tensors to the same device. So here I'm doing exactly that. After getting the inputs and labels from the data loader, train data loader or validation data loader, I'm putting those into my device, which may be GPU or CPU if GPU is not available. And then optimizer.zeroGrad, because for every mini batch during the training phase, we typically want to explicitly set the gradients to 0 before starting to do backpropagation. And then my entire forward propagation is this will start with this code, this line here, with torch.setGrad enabled phase equal to train. So this setGrad enabled, this is a context manager that sets gradient calculation to on or off. The argument to these setGrad enabled is a boolean. It's called mode actually, and this mode controls whether to enable grad, that is if it is true, and whether to disable grad if it is false. And this can be used to conditionally apply it, and that's what I'm doing here. I'm conditionally setting the mode here. So if phase equal to train, this will be in that case it will be true. That means the grad will be enabled. But when this entire loop will go through the validation phase, because I am that's what I'm looping through, that is for phase in train and validation. This whole code is being looped through these iterator. So when the validations is activated, then this will be false, and in that case gradient will be switched off. And after setting the gradient to enabled, the first step inside my forward propagation is to calculate my predicted outputs, and which is just my these simple line model inputs. That is, to my model which is already there, I am passing inputs. That's it, and that will give me the prediction. And that's what I'm getting in this predicted outputs variable. And now from these predicted outputs, I have to find my predictions, that is actual predictions. So to get my actual predictions, I have to apply these torch.max. And again, these are all pretty standard code. You have to first get outputs and then apply torch.max. To that, you have to pass as the first argument as these predicted outputs, and then you have to pass the dimension. Dimension could be most of the cases it's 1. I will explain it in a second that why it's so. So this is pretty standard code in most of PyTorch neural network implementation. You will find this kind of signature and this kind of structure when you are calculating the predictions from your model and then getting the maximum value from those predictions. And of course, this is applicable for multi-class classification problem, where first I will get a probability tensor, and from there I have to find the max value to get which class has the highest probability or the maximum probability. Now quickly check how torch.max function works, so that we will understand that how this is getting my prediction, the maximum probability, and also why I'm using these input dimension, the dimension to be 1. So let me go to my VS Code, and what I will do is create a random matrix. I will just paste a code here. All right. So this is my, why I'm getting this rand. It should be added to my VS Code spell dictionary so that it does not get flagged as wrong spelling. Anyway, I'll look into that later. All right, so this is my code. What I'm doing is I'm just importing torch and then creating a random matrix of 2 by 3, that is 2 rows, 3 columns with torch.randn function. And what this will do is this will randomly, it will take a size and generator. Okay, anyway, that's not important. So basically this will create a random matrix of size 2 by 3, and this let's say that this matrix is created, or this tensor is created, and this is a two-dimensional tensor. I have 2 rows. Let me put it slightly in a better way. I have 2 rows and 3 columns, and then I am applying, I need to get the maximum from each row with torch.max. And so in this next line, what I'm doing is max element and max element index. It will find my indexes of this max element. So torch.max, and I am passing them to this vector, this tensor p that has been defined here, and dimension I'm giving 1. I could just put without this named parameter, I could just put 1 as well. It's the same thing actually. And then if I print these max elements, that will give me maximum from each of these rows. So what is the maximum from the first row? That's 1.2559. So from this line's output, I am getting 1.2559. And for the second row, the maximum element is this, and that's exactly what I'm getting as a second element. So max elements, which is an output of torch.max, gives me the maximum values from each row. Why I got from each row? Because I have mentioned dimension equal to 1, dim equal to 1. If I mention dim equal to 0, that would be the column wise. So then from each column, it will give me the maximum value. And what is this max indexes? It is just the index number of these maximum elements. So for the first maximum element 1.2559, what is the position or index number? That's 0, because it comes at the 0th position in the first row. So I get max index, the first one is 0. And for the second element 1.3895, that's the second 1th element of my second row. So max indexes second is giving me 1. So basically torch.max will give you the maximum elements and also the positional index number of those maximum elements. That's how it works. Now get back to my Colab. And after I get my predictions by applying the torch.max, now I apply the criterion to get my actual loss. And what is our criterion? We already have defined at the very top. Let's go back and see. Yes, criterion is nn.cross entropy because it's a multi-class problem, so we are using cross entropy. All right, now, so to my criterion, I give these predicted outputs and the labels. So both of these I have already by now, and this will calculate the loss. So this pretty much is the prediction numbers, and this is the ground truth numbers, and that will give me the loss. And then for the train phase, I have to start now the backward propagation. So for that, I am doing this little thing that if phase equal to train, then loss.backward, and then also optimizer.step. Standard code, that is, you run loss.backward and then do optimizer.step. And what does optimizer.step do? It updates all the parameters based on parameters.grad. Now, when you call this loss.backward, all it does is compute gradients of loss with respect to all the parameters in loss that have requires grad equal to true, and store these gradients in parameter.grad attribute for every parameter. And then I'm doing optimizer.step, so this will come and updates all the parameters based on parameters.grad. That's how it works. And now a very important step, running loss calculation. Let's quickly understand how these logic goes here, and then we can understand that why I am doing input.size 0, and then I'm also doing a torch.sum. First, note that in running loss, I want to capture the total loss for this batch, and that's why I am doing this plus equal to by accumulating over the entire batch. As soon as a single loss is calculated, I'm adding that loss to it. Now, why I am doing loss.item and multiplied this loss.item by this input.size 0, and that's because first of all, what is loss.item? You cannot use loss directly because the loss directly derived from this criterion is a grad function and not a float number of Python. Hence, you do loss.item to extract the losses value, the scalar value, as a Python float. And now going back to the point that why I'm multiplying this loss.item by input.size 0 is because this loss.item contains a loss of entire mini batch but divided by the batch size, that is the number of samples per batch. That's typically how PyTorch returns you the loss. It's because for most of the function, for most of the loss functions like cross entropy and all, this loss number will be an average loss number. That's how PyTorch will be reducing this loss number, and you can see the documentation for this purpose. And that's exactly the reason for I have to somehow unaverage this loss, and that's the reason I'm multiplying by the batch size, which is my input.size 0. And this input.size 0 would give me the total number of samples for this batch, which is the total number of images in this batch. For this particular notebook, it's I have kept it at 32. You can see that at the top I have defined a variable called batch size, and that's been defined to be 32. So, and after you calculate the running loss, you also have to calculate running accuracy or running corrects. So this variable will hold how many corrects were determined, and that's simply equal to torch plus equal to torch.sum predictions equal to labels.data. And our predictions you already have calculated here with from torch.max, and when that is equal to my ground truth, that is labels.data, I'm summing over all these values to get my running corrects. All right, so at this line, my batch calculation loop gets over. Remember, again, I'm running two loops. The outer loop is for epoch in range number of epochs, and within that I'm running another loop for all the batch calculation. That is when I'm looping through the data loader, train data loader dataset here. So all these calculation for this block gets over here. That is, all my batches are calculated here for a single epoch. That means I'm ready to calculate the epoch statistics after this line, and that's what I'm doing here. So before calculating the epoch statistics, I have to adjust my learning rate, and so I do that with scheduler.step, and obviously you have to do this only for the training phase and not for the test phase, and that's why I'm using this if condition here. All right, and my epoch loss is simply my running loss divided my dataset size, dict, and phase. So that will give me my train dataset length or test dataset length depending on which phase I am in. And to check this variable again, we already have defined it earlier, and that variable was this, that we defined a dict for both dataset data loader dictionary and also for dataset size dict, where I have the length of the train data loader and also the length of the validation data loader for my train and validation phase respectively. All right, now, so that become my epoch loss, that is total accumulated running loss for all the batches divided by the length of my training or test, and also my epoch accuracy, that would be running corrects. I have to convert it to double, and then again divide by dataset size dict, and then the phase. Phase will be either train or validation. All right. So these two lines of code, that is a running loss and running corrects inside the batch loop, and epoch loss and epoch accuracy outside the batch loop, but for this particular epoch, this two piece of code is very important. So let's summarize this at what I did in between these two pieces. So inside the batch calculation, I multiply each average batch loss with the batch length. And what is my batch length? This is input.size 0, and this gives the number of total images in each batch. Essentially, I am unaveraging the batch loss because PyTorch returns you this loss as an average loss for this batch. Now do this for all the batches inside the batch running loop, and then after the batch running loop, that is outside of the batch loop and coming back to my epoch loop, I am doing these two lines of code. Here, divide these accumulated running losses, which is unaveraged batch loss from all batches, by the number of samples, that is the length of my train data loader, to get the exact train loss average for this epoch. And now that my epoch loss and epoch accuracy has been calculated for this specific epoch, I can update my training history and validation history variables. Remember, we already defined my training history and validation history variables here to be a dict, and it will have an accuracy key and a loss key. Similarly for validation history, accuracy and loss key. So update these two variables with my loss and accuracy. So if phase equal to train, then train history loss. To that, I'm just appending epoch loss, and training history accuracy, I'm appending epoch accuracy, and exact same thing for my validation phase as well. So that after that, finally update best accuracy and deep copy the model. So if phase is validation and epoch accuracy is better than best accuracy, we already defined our best accuracy, I think, to be that was initialized with 0. Yes, best accuracy was initialized with 0. So now with each epoch, I'm going on to update that. Yeah, and the condition is if this epoch accuracy is better than the previous best accuracy, just update my best accuracy to be equal to this epoch accuracy. And I'm also creating best model weights equal to copy dot deep copy model and dot state dict. All right, now just time after all this time elapsed is time at the end of it. That is time elapsed is time now minus start time. All right, so that's my training, and finally after all the epochs are done, I have to load my best model weights, and I can load that because for the entire thing I was going on saving it in state dict. So now I can use model dot load state dict, and to that I can pass this best model weights, and finally from this entire train function, I am returning the model. That pretty much it. And then in the next cell, I just have to invoke that train function. That is this the entire train function that we defined here in this cell. I'm invoking that in my next cell. To that, I'm passing my model, my criterion, optimizer, learning scheduler, number of epochs. I'm keeping it at 150. You can actually run it with 10, even 15, or even 7 or 8. You will see pretty good result. I was just going to the extreme of running 150 epoch, and after running 150 epoch, let's see what kind of, okay, after running 150 epoch, yeah, I have to explain another cell, that is my evaluation, and then we will see the result, the final result of the 150 epoch. So this is my evaluation function on my test dataset. So I'm defining a function def evaluate, and this will evaluate the entire trained model on the test dataset. Remember again that in our dataset we had two sets, train and test. So the purpose of this evaluate function is to basically determine if the for the test data set, the classes are predicted correctly after applying the trained model that we got above. So let's understand these evaluate function, the way that I'm building it. So overall, some of the structure remains very similar to my train function. That is for this part where I have to calculate the prediction, and I have to calculate the correct values predicted, etc. So let's go line by line. First, I'm defining some standard variable, that is a loss on test dataset. I am initializing to be 0.0. Correct class is just a list of my for my class categories, and similarly total correct for all classes, and just as the name suggests, the correct class is for each class, and total correct for all classes is the list for all classes together. And obviously then I am doing this line because now I'm in the eval mode, I'm no more in the training mode. So this is very important for any evaluation code. And yeah, so then I'm starting this loop. That is, I have my test data loader, and then I'm looping over these entire test data loader. And just like my train data loader, this test data loader as well will return me batch by batch the entire test data set. And what is my batch size? That's set to be 32 for this notebook. So when I'm looping through TQDM test data loader, I will get test inputs, images, and test labels. And then the standard code of checking the availability of the GPU, and if GPU is available, that is CUDA.isAvailable returns true. Then I'm making use of the GPU by doing test inputs and test labels to be equal to test inputs.CUDA and test labels.CUDA. And then because it's the whole function is for evaluation, I do not need gradient calculation because I do not want to update my weights definitely. So I am doing this, that is with torch.noGrad, then all my calculation for the model invoking goes on. That is with torch.noGrad, I'm invoking the model, and this model is the only argument to this evaluate function. And this will be our trained model that has already been trained on my train dataset. And to this model, I'm passing the test inputs, all my test input images, and that will give me my output test. And then the loss calculation by applying the criterion function, which is in our case nn.cross entropy because it's a multi-class problem. And these codes are pretty standard. What we saw in the train function, that I calculate the loss by giving to the criterion function this output from the model, and also the ground truth, which will be my test labels. And because this loss is an average loss, I have to unaverage it by multiplying loss.item with test inputs.size 0. And then I apply so this will give me my unaveraged loss, and I also have to find the exact prediction on the test. For that, I have to apply the torch.max on the vector output test vector, and with a dimension of 1, because I want to get the maximum probability value across each row. We discussed this in detail in the train function. All right, so that now I have loss on test dataset. I also have the pred test variable, which will have my actual predictions. Now compare predictions to true level. That I will be doing with this line. Correct tensor equal to pred test dot eq. This is a PyTorch function to compare two tensor element wise. So pred test.eq, then I have to pass the test labels. This is also a tensor, but I have to use a view as pred test. So let's understand what the equal does first, and then I'll come to the view as. So to compare two tensor element wise in PyTorch, we use this torch.equal method. It compares two corresponding elements and returns true if the two elements are same, else it will return false. And we can compare two tensors with same or different dimensions, but the size of both the tensor must match at non-singleton dimension. So you just go through the documentation, you will see some examples. And the view as, this this view as will just do as it says, that view this tensor as the same size as the other. So self.view as other is equivalent to self.view others.size, because I want to compare pretest tensor with test label tensor. So I have to convert these test labels to be the size of pretest. That's all it is. All right, now this correct tensor will give me a tensor with true false values. That is a result of this equality test. And then I am defining a variable called correct by squeezing this correct tensor and making use of CUDA again. And what is squeeze? Squeeze is just it will clean up your tensor. So let's quickly see an example of squeeze. So the squeeze helps you get rid of useless one-dimensional arrays. For example, instead of using this array, which is a three-dimensional array but containing just a 789, it will clean it up and squeeze it to be 789. And then again, take an example of this one. This looks like a four-dimensional here, but it is simply a two-dimensional array actually. So squeeze will make it like this. That is, this four-dimensional unnecessary, all this unnecessary dimension will be squeezed and taken out, and my output from the squeeze will be this. All right, and that's why I'm squeezing it here, to clean up unnecessary dimensions from my correct tensor. Because it will compare two multidimensional tensors, and it will probably have some extra dimension which are completely unnecessary. That is, the dimensional value will just be 1, and I do not want that in my correct. And because correct, I'll be using this correct in further calculation downstream. All right, now that I have the correct, which is the tensor containing the true false values of my correct prediction on labels, now I will be calculating the correct class and also the correct for all my three classes together. So a quick if calculation: if test labels equal to batch size, then I'm looping over the batch size, iterating through the batch size, I in range batch size. Label is test label dot data dot I. This is obvious. I'm getting label of this particular index. Then correct class label, that I have to update this correct class correct class variable, which will contain the corrects for each class object. And I will have another variable, this total correct for all classes, that will have the corrects for total classes. So in these two lines, I'm just updating them with correct.i.item, and then I am also updating total correct for all classes. Label will have the label plus equal to 1 if it's correct. Then finally, just calculate the loss on the test data set by doing the exact same calculation that we did in my train function. That is, loss on the entire test data set divided by the length of the test data loader dot data set, which will give me the length only on the test data loader part. That pretty much completes it, and the rest of these are just properly calculating the final prediction accuracy and printing them for both my individual classes. Remember, we have three classes, which are they are my COVID, normal, and viral pneumonia. So now I want to print the accuracy for each individual classes, and also I want to print the accuracy of all the classes together to get an overall view. So in the first loop here, I am printing the each classes, that is correct classes I. So I'm doing a little loop here for I in range lane class categories. Then if total correct for all classes I, that is if this correct is more than 0, then I am printing them, that is printing the test accuracy of this class category multiplied by 100, because it's a percentage value, it will be in a decimal value, so I have to multiply by 100, and then multiplied by that total class correct I divided by total correct for all classes. And if this is not more than 0, that means something wrong. So in that case, I will just print test accuracy, no training examples at all. And then in the second one here, I'm just printing the total accuracy, that is for all classes together. And finally, I am invoking this evaluate function, passing it my trained model trained variable. This is the variable that was there here. It's coming from here when I train my model. So this is output of my train function. And I'm just simply passing that to my evaluate function, and that will give me this evaluation. So after 150 epochs of training with this very simple efficient net B0 pre-trained model, I got an accuracy for the COVID class of 92%. For the test accuracy, I got for the normal class I got 89, and for the viral pneumonia I got 100% accuracy. And overall my test accuracy for all these three classes together is 93.75, which is not bad at all. That pretty much wraps up this video, and all my upcoming videos will all be on some great computer vision projects and algorithm with PyTorch and Tensorflow. So stay tuned, and if you have not subscribed yet, do subscribe. And if you like this video, smash the like button. Thank you for watching.